Good afternoon. Welcome to my talk. Um, I was reminded of what Albert said about, talking about geoengineering versus climate interventions, and I generally talk about climate interventions. So, as you know, this is about marine clouds, and what I want to bring home today is really the message that what happens at the small scale is really important if we want to understand how effective marine cloud threatening could be. But as a caveat, obviously, that's only a small piece of the puzzle, right? But I'm going to talk mostly about like those small scale processes for today. So marine clouds, just to give you an impression. So this is a satellite image of some marine clouds, and those squiggly lines are ship tracks. So basically, we're thinking about producing artificial ship tracks, right? And as you can see, this is like 100 times 100 kilometers or so. But what we want to know is what happens at a scale of, say, centimeters or meters, right? And that is important because at the core of marine cloud brightening, what happens is that you have particles, those make droplets, and that makes the clouds more reflective, right? But as I said, it's not that you have those processes only in isolation, but obviously, because if you interfere over a larger area, you will also have impacts, for example, on atmospheric circulation. But this is not what I'm going to talk about. What I wanted to highlight here as well is some people have thought about exit ramps for the physical part of marine cloud brightening. So the things or the topics that we need to nail down and that could lead us to saying, okay, marine cloud brightening is maybe not a good option for us. And what you can see here is, for example, the cloud microphysics. So this is how a droplet or droplets form in clouds. And the other part is that I want to touch upon is like, how do those particles that we produce, say at sea level, actually get to cloud altitude and are able then to form a cloud, right? But then, there's also those other options. How would we even know that this intervention was really successful? And where are really the regions where we could successfully do those interventions? And as I mentioned, you would also have impacts on the larger scale circulation, on precipitation patterns, and all that. So that is something that Michael mentioned in his talk. And obviously, where you also get like into more the policy sphere, right? Even though we're talking about physical sciences, is when you talk about the impacts on the marine ecosystems. That's why I was saying that I'm talking about the small scale processes, but they're only a small part of the puzzle, right? So this is what I wanted to bring home here. So what we did is with a couple of experts, we thought about like what are really in modeling the key uncertainties that currently prevent us to have like a good and robust assessment of marine cloud brightening. So we do have some indications from global climate models that Michael mentioned that this could work. But as we also mentioned is those climate models are incredibly coarse scale, right? So what are the processes that we would like to capture better in order to have a better assessment of marine cloud brightening? And let me start from the bottom, even though that's number 2 here in our graph. And that is, if you just think it through, right, you would have some kind of vessel. So, for example, like the ones that our Australian colleagues are using. And those vessels would spray particles, right? And those particles, they wouldn't stay here, but they would need to get transported to cloud altitude. But then the second part that you have is that those particles, as Michael also mentioned, they need to have the right size, whatever that means, right? But for now, let's just say they need to be really, really small. So think 100 nanometers or so, which is like a significant engineering challenge, as I will highlight a little later. So how we model those size distributions of the particles that we add to the cloud is also something that we need to get, right and informed by data. So in that case, by real laboratory data from our colleagues. And the part that I'm going to skip in my talk is, as I mentioned, what happens else in the cloud. Because what happens is that you get the increased albedo if everything works out. But then, because you have larger scale or local scale circulation responses, it might also be that you redistribute humidity within the cloudy region, right? So you will also have effects potentially on other regions. So, and that kind of, highlights that this is a very interlinked and interconnected system, right? So, That's that for like caveats and introduction for now. So, um, because Michael didn't have a lot of time to go into this, and for like the non-cloud physicists among you, which are a lot, I guess, what is a cloud actually, right? So a cloud is something that forms on particles, and those particles they get lofted into the air. And during this process, they accumulate humidity and form tiny droplets, right? So this is why this parameter, so the updrafts, is important because it kind of governs like how high the humidities can get within an air parcel, and also how much time the particles and droplets have to grow. So this is why this is important for cloud formation. And the other factor is it's also important how many particles you have around, right? Because if you have like a very dirty background condition, so lots of particles around, that means that adding some more particles doesn't give you as much bang for your buck, right? Because there's already particles that can make a cloud if we want to simplify it. So this is why we considered those two factors in our small scale modeling, and we had the pleasure of working together with some colleagues from Cambridge, just to name Sean here, and I don't see Hugh in the audience. And there's obviously Dante and lots of PhD students sitting in the waiting room. And together with those, we really tackled this engineering aspect. And what we got from them were the size distributions that I mentioned. So having realistic size distributions for the sprayers to do this kind of modeling, how the cloud would develop, like as a first order approximation. So this is something that Zach did in his work. And as I said, he looked at those two parameters. So like how fast does a cloud go up? So how vigorous is it? And how much is the background pollution? So W and NVG is what he varied. And he did that for three different size distributions that he received from our colleagues who did some incredibly great work on spare development as of now. And what he got was this here. So this is a bit busy, so I'll just walk you through. So the parameter that we're looking here is the change in albedo. So basically, how much brighter does the cloud get? So big is beautiful, so we want to have a lot, right? So the bigger the number, the better. And the first thing that I'd like to highlight here is if you look at the very polluted conditions, what you see is two things, basically. The lines, so the different albedo changes for different stereotypes don't differ that much, right? So that's number one. And then also the dynamics of the clouds don't matter too much, right? Under those very polluted conditions. So that means that in reality, if you were to spray in a polluted cloud, it doesn't really matter like what you do, if I simplify. However, if you're in relatively clean conditions, so NVG is relatively low, what you can see is both you could have a difference between the sprayers, but you could also have a difference, in the updraft velocities. So at clean conditions, like how you spray and what the dynamics are in the cloud become more important. So that's one message. So essentially, it really depends on like under which conditions you spray, how you spray, and what the dynamics are within the cloud. Zach repeated those simulations with the second type of simulations. And this time he assumed, as you can see here, is he had basically, no bounds on energy consumption, let's say. So you can just spray a lot, as much as you want, basically. And then it really doesn't matter like what you do essentially, right? So if you're not energy constrained, you're also lucky. But in the real world, as our colleagues very well know, energy consumption is unfortunately a real concern if you want to design spray as well. So that's just what I wanted to highlight here, that, really those very fine details of modeling and how the processes work matter a lot if we think about, how to cascade the uncertainties from those processes then into larger scale simulations. So it really matters what happens at the smaller scale. So that was basically our first learning. And for the second one, as I said, in the global climate models, the processes how those particles get to the cloud are very simplified, right? So basically, they're just there. However, in reality, you would have a spraying vessel like the one you saw from our Australian colleagues, and those particles need to get up, like from the ground to cloud altitude. So, which means that you also have the whole plume dynamics and potentially also multi-plume dynamics that you need to consider if you want to understand what happens. And one of the surprising things were that when we tried to model a plume, so like a single source, and how that plume then develops, that the evaporative cooling that is produced during this process, so that the plume goes up and then cools, that actually matters of like for how many particles get to cloud altitude. So as you can imagine, that really depends on the parameters of your simulation. But we saw that, this plume dynamics could have a real impact on how many particles actually get to cloud altitude. So this is something that we're investigating in a bit more detail. So what you can see here is like the source and the plume and how it develops basically. And there is a significant difference whether you include evaporative cooling or not. So also at that stage, so if you think about like larger domains, say kilometer scale, those dynamic processes at the smaller scale still matter. Um, so what we learned in our project that we did with our Cambridge colleagues, funded by the Refuse the Arctic Foundation, was that really linking engineering and science brings an immense value in our ability to really simulate marine cloud brightening, and also that we need to do a lot more studies looking at this very small scale. And then just a small ad. We have two posters. We have obviously more posters also, but these are the atmospheric science one by Annalot and by Zach. So please come and visit them. Thank you very much.
Thank you so much, Isabel. So we have about 7 minutes for questions. So questions for Isabel.
So, hi as well. What makes the different sprayers more effective or have different effectivenesses for different concentrations of pollutants or updrafts? Because not one sprayer was the most effective for all of the scenarios.
Yeah, so one difference is really in the size distributions. So if you remember, the size distributions have different medians, so like how large most of the particles are, and then also how broad the distribution is, right? So for example, if you had a larger tail, that might be that that has negative effects, for example. And then also within those very simple model simulations, only like a certain part of the particles activates ideally, let's say. So those are the differences.
Hello. Thank you for your talk. If you could go back to the beginning of your presentation regarding knowledge gaps, I'm curious how accidental marine cloud brightening from industrial shipping emissions can help address some of those knowledge gaps.
So, I mean, that is a large field where we try to use also existing shipping emissions as opportunistic experiments to learn more about how additions to the aerosol population would impact the formation of clouds. So that is kind of an existing field. And but the thing is obviously from the ships, so that aerosol distribution is not very controlled or constrained, right? And the added difficulty here is that we can do that with satellite observations, but then our knowledge of the true size distribution from those like very polluted plumes is also somewhat limited, right? So to be taken with a grain of salt. But yeah, there are ideas about using ship tracks, about using, for example, dust events and all that to really understand how clouds form in nature. Yeah.
Any more questions?
Thank you. Florent Richter from University of Montpellier. You spoke about the physics of the clouds, but what about the chemistry? I
Mhm.
saw a couple of papers saying that marine cloud brightening will increase the lifetime of methane through chlorine atoms, destroying tropospheric ozone and reducing the amount of hydroxyl radicals, and then destroying less methane.
Yeah, so maybe 2 points to that. So chemistry, so first of all, we're like really low in the boundary layer, right? Say like up to a kilometer or so. So we don't necessarily impact processes higher up in the stratosphere. However, through dynamical processes, it might be that there's some effects. That's one thing. The other thing is that if you add particles, and especially maybe if you divert from sea salt, you might have some heterogeneous chemistry going on there, right? So that is a possibility. And the third thing where chemistry is even more important is that the composition of the particles governs like how active they are as droplet forming nuclei, right? So this is kind of like the foremost important factor that we'd like to consider as well, right? Especially when it also comes to thinking about the background concentrations, right? Because you might have pollution in there, and those might have different hygroscopicities than, for example, so they're like not so water loving or more water loving than other particles. So that's something where chemistry is really important, I would say.
I think my question follows up on the previous one.
Yeah.
So I guess the question is about the generation of hydroxyl radicals, right? Yeah, I wasn't sure if I understood
Mm.
your response, because I think the process happens throughout the column, and I don't know whether reflecting it back, traveling through a thicker portion of the troposphere that's thicker, let's say from
Yeah.
3 to 10, maybe that
Mhm.
actually enhances. So that depends on the transfer function of the wavelength distribution of the downwelling versus upwelling light
Mhm.
through the cloud reflection. So I
Yeah.
don't know if there's what's the spectral change through this?
Yeah. So that's not something that we've been looking at, honestly. And as I said, there are some chemistry implications, and the one that you mentioned, might be important, but I'm not aware of it right now. And because we're looking mostly on like the dynamics and the physics, it's not something that we've considered as of now. But as I said, also, for example, like with the marine ecosystems, all those processes, so chemistry, dynamic, so larger scale dynamics, impacts on ecosystems, are something that we would need to consider, like, once we get a grip on the physics. So this is kind of the sequence we're following as of now, right? So I don't want to exclude that atmospheric chemistry plays an important role. It's just not something that we've investigated in detail. So
One last question as well from John Moore.
yeah.
Yeah, I would just kind of like to get your view on relative sizes of what you're doing compared with the kinds of places, for example, I worked in Beijing for 10 years, and that's a super polluted, or it used to be,
Mhm.
environment. Of course, you have huge volcanic eruptions like happened in Iceland that changed the cloud condensation
Mhm.
properties very markedly, you could see from satellite. And these are very tiny things that you're doing.
Mhm.
So can you in fact learn just as much by studying the things in nature, or do you think what's the advantages of doing these small scale experiments compared with looking at nature?
So, I mean, I've been talking about simulations, right? So your question is, if I paraphrase it, like whether there's value in like doing it in real life, like with a sprayer. Did, did I get that
Yeah,
correctly?
yeah, but well, I mean, kind of putting it in perspective that though nature does massive experiments in a
Yeah,
sense anyway,
yeah,
and kind of can't you I'm not kind of criticizing what you're doing, but
yeah.
I'm saying that the signal to noise ratio in those natural experiments is so much
Mm,
better.
yeah. No, I think I'm going to give like a general answer to your question. What is totally true is that no matter whether you want to look at like opportunistic experiment or field experiments in the future, what you definitely need to know is have a solid baseline, right? So you're totally right that at least, that's a start. And then, hopefully your signal will be large enough. But I think getting a baseline first, which means that having good quality observations over longer times over the oceans. So think of aerosol concentrations, so in situ, not only from satellites, and then also having like cloud properties, having radiative impacts of those clouds. I think that's something that is needed. And I think especially at the in situ part, we're kind of missing. So we don't really know how the aerosol concentrations really behave close to the ground, right? And I think that would be also a necessary prerequisite for doing, field experiments and for also improving our knowledge about those opportunistic experiments. But those are super expensive, so looking for funding.
Very much, Bill.
Mm.